On May 26, 1940, the early production Supermarine Spitfire, Mark 1A, serial number N3200, was hit in its radiator during combat. It had been issued to No. 19 Squadron at Royal Air Force Duxford in April 1940, only a little over 5 weeks before its loss. The sortie on May 26 was its first and only operational combat mission. Squadron Leader Geoffrey Stephenson led No. 19 Squadron on a patrol to cover the evacuation of Allied forces from Dunkirk. The flight profile demanded maximum performance from the aircraft to intercept and engage hostile targets. The early Spitfire design prioritized absolute aerodynamic speed and agility, achieving this through a streamlined airframe that tightly cowled the internal components, including a liquid cooling system that had to shed heat through the airflow beneath the wing. The Rolls-Royce Merlin power plant driving the aircraft is a high-output liquid-cooled engine. It requires a continuous, pressurized flow of coolant fluid circulating through the engine block to absorb the extreme heat generated during combat maneuvers. To shed this heat, the heated fluid is pumped through a radiator matrix mounted beneath the starboard wing. This positioning places the radiator directly in the high-velocity slipstream for optimal cooling efficiency. However, this optimal aerodynamic placement also leaves the radiator vulnerable to combat damage. When enemy fire ruptured the radiator on N3200, the closed loop was broken and pressurized coolant vented from the damaged tubes into the external airflow. Inside the cockpit, the first warning would be falling coolant pressure and rising temperature. The engine could continue to run for a short time, but the loss of cooling threatened the pistons, cylinder walls, bearings, and oil film that kept the moving metal surfaces separated. As the heat built, the internal lubricating oil would lose its ability to protect the engine. Friction would rise, power would fall, and the pilot would face the risk of the Merlin tightening and seizing. Once the engine stopped producing useful power, the propeller ceased to be a source of thrust and became drag. The Spitfire was no longer a powered fighter. It was a dead-stick aircraft losing altitude over enemy-held ground. The complete loss of thrust imposes an immediate kinematic constraint on the airframe. To maintain the forward airspeed necessary to keep the wings generating lift, the pilot must aggressively push the nose down. This maneuver permanently trades precious altitude for airspeed. The glide ratio of a fully loaded fighter aircraft with a stationary propeller is severely limited. Every slight adjustment to the flight controls and every degree of bank angle bleeds kinetic energy that the pilot cannot recover. N3200 had been on the active roster for just 5 weeks before a single point of failure ended its service and pulled it out of the defensive formation. With the internal combustion engine seized completely solid over contested geography, how could the pilot trade his rapidly depleting altitude for a survivable outcome? For more than 45 years, the physical structure of the downed fighter remained locked beneath the surface, hidden beneath the French sands. The transition from an airborne machine to a buried artifact began with the forced landing decision. This dead-stick, wheels-up beach landing forced a rapid procedural decision. The pilot had only one chance to convert his remaining airspeed and altitude into a survivable glide slope. Stephenson selected the tidal beach at Sangatte, near Calais, and brought the aircraft down there. To prevent the landing gear from digging into the soft sand and violently flipping the aircraft over, the pilot kept the manual undercarriage retracted. The aircraft skidded across the wet beach on its belly. The structural integrity of the fuselage held together, and the airframe survived the impact largely intact. Following the successful ditching, the aircraft was immediately immobilized on the exposed tidal flat. German soldiers reached the site, and period photographs show them posing with the downed Allied aircraft. However, the heavy structural shell remained in place. The beach was not a static parking surface, it was a highly active geological zone. The dense metal airframe rested on wet sand, and the repeated action of tide and sediment steadily worked the wreck deeper into the beach. Within a short period, the shifting sands completed the intertidal burial mechanism, sealing the fuselage beneath a preservation boundary that also hid it from wartime recovery. But the same matrix that protected the aircraft from recovery also imposed a chemical penalty. The intertidal zone subjected the buried aluminum to a relentless cycle of saltwater saturation during high tide, followed by partial oxygen exposure during low tide. This environment was brutal for an aluminum airframe. Saltwater and wet sand attacked the metal over decades, leaving extensive corrosion, pitting, and structural uncertainty in the spars, skins, ribs, and bulkheads. The aircraft remained trapped in this state of continuous corrosion for 4.5 decades. The physical equilibrium of the beach held the wreck underground until 1986, when strong currents and shifting sands exposed it again. The protective sediment layer was breached, and sections of the degraded airframe reappeared in the open air. The reappearance of the fighter created an immediate, time-sensitive recovery window. The same tidal forces that exposed the metal could easily destroy it or swallow it again during the next tide cycle. The wreckage was excavated and recovered from the Sangatte sands in 1986, then removed from the beach for display. The recovered artifact was extremely fragile, deeply pitted, and structurally compromised by 46 years of marine decay. Yet the recovered wreck remained largely intact in outline, preserving enough of the early Mark I form to become a crucial physical reference. It was not a flyable structure, it was a damaged survivor whose shape, surviving fittings, and remaining original material could still inform the historical record. What happens to a highly corroded 1940-era aluminum airframe once it is suddenly pulled back into the oxygen-rich atmosphere? Upon extraction, the airframe presented a contradiction. It still resembled a complete fighter, retaining its unmistakable profile and major structural components, while the metal beneath that profile remained too degraded for immediate engineering recovery. The groups who initially secured the wreckage lacked the heavy industrial facilities required to halt the deep internal degradation or to begin a complex mechanical overhaul. Instead of entering an engineering bay, the fragile shell was transported inland to a local exhibition space known as the V3 Museum. For several years, the remains were displayed at a local museum, including the Mimoyekes V3 Museum. In that period, the airframe was still a displayed wreck rather than an airworthy restoration project. The ownership phase changed in the year 2000 when Mark I partners acquired the remains. The airframe did not immediately become a flying machine. It was moved into storage, and the recovered structure later arrived at Duxford in 2007. Only after further research and preparation did the restoration move toward airworthy reconstruction, with work commencing in 2012 at the Duxford facilities associated with Historic Flying Limited and the Aircraft Restoration Company. Before any mechanical work could begin, the engineering teams had to establish a rigid proof of identity and a baseline of structural integrity. They initiated a comprehensive physical audit of the entire machine. This required inspecting the decades of accumulated dirt, marine growth, and loose debris to map the bare metal underneath. The engineers meticulously documented every surviving rivet line, bulkhead frame, and wing spar. The primary goal of this audit was to determine exactly how much of the original material could withstand the extreme aerodynamic forces of active flight. The baseline assessment required strict evidence discipline to separate viable metal from dangerous, degraded material. The results of the engineering audit confirmed the contradiction that had been present since the extraction. The surviving structure proved the identity and early production character of the aircraft, but the saltwater environment had been harsh to the aluminum. Much of the original material could not be trusted for primary flight loads, and the team had to decide, piece by piece, what could be retained, what could be documented, and what had to be newly manufactured for safe flight. Those findings dictated the next procedural phase. The aircraft could be rebuilt only by separating evidence from structure and authenticity from load-bearing safety. How could a team rebuild an airworthy fighter when so much of the original aluminum could not safely carry the loads of flight? The answer began with a disciplined change in restoration methodology. The team could not simply patch the localized holes and declare the wreck airworthy because new metal and degraded old metal do not carry load in the same way. The historic airframe had to be documented and dismantled where necessary, with original parts retained wherever they could safely and authentically be used, and other parts treated as references for newly manufactured replacements. This process of forensic template extraction is a highly delicate mechanical operation. When an airframe is structurally compromised by corrosion, its surviving dimensions must be accurately captured before the metal crumbles or bends. The Duxford technicians had to dismantle the aircraft without altering the physical shape of the individual parts they were removing. Standard aviation disassembly techniques often involve drilling out rivets with heavy pressure or forcefully prying overlapping skins apart. However, applying standard mechanical force to corroded 1940 aluminum would cause the thin sheets to warp, stretch, or snap entirely. If a bulkhead or a wing rib bent during extraction, its dimensional data would be permanently corrupted, rendering it completely useless as a master production template. The team therefore used extremely precise extraction methods. Corroded fasteners were carefully isolated and removed with minimal kinetic impact to the surrounding skin. As each piece of the fuselage and wing structure was safely separated, it was immediately mapped and measured. The engineers recorded the distances between structural rivet holes, the curvature of aerodynamic skin panels, and the angle of internal brackets. The value of the wreck was not that every dimension was perfect. Its value was that enough original evidence survived to guide the reconstruction of a very early Mark I aircraft whose details differed from later Spitfires. Using the successfully extracted dimensional data, the technicians began manufacturing replacement parts from newly milled, modern aviation-grade aluminum. They placed the heavily pitted original part on the fabrication bench and built a brand new duplicate directly beside it. Each new component had to convert that evidence into an airworthy part. If an original wing rib featured a specific tool clearance hole or a unique 1940 manufacturing bend, the new piece was formed to reproduce that geometry. The result was a strict parallel construction process. New load-bearing metal shaped by original evidence, with surviving original parts retained wherever possible. The rebuilt skeleton gained the structural strength required for flight while preserving the early Mark I configuration. Capturing the exact shape of the surviving metal was only the first step. How would the team handle components that standard restoration supply chains no longer produced? The engineering team at Duxford reached a critical trade-off edge during the fabrication phase. Standard restoration practice can sometimes draw on components from later production blocks, because later model parts may be more available, mechanically standardized, or easier to maintain. For N3200, that shortcut would have diluted the historical accuracy of the machine, so the project followed a strict original specification restoration brief and moved into the reverse engineering of extinct mechanical systems. The most demanding mechanical challenge dictated by this original specification brief was the undercarriage retraction system. On later aircraft, an engine-driven hydraulic pump raised and lowered the main landing gear. The early Mark Ia specification retained a hand-operated undercarriage pump on the right side of the cockpit. After takeoff, the pilot had to select undercarriage up and pump the handle to raise the wheels into the wings. Because this manual pump system was an early feature later replaced by engine-driven operation, the Duxford team had to recreate it from surviving evidence and specialist machining. Drawings, surviving evidence, and specialist machining guided the recreation of the hydraulic valves, linkages, and mounting brackets, so the system would look correct for 1940 and function safely in an airworthy aircraft. The same standard shaped the airframe's other specialized components. The aircraft used the early de Havilland 3-blade variable pitch propeller appropriate to N3200, rather than a later constant speed arrangement. It also retained the flat-sided early canopy form. This enclosure offered less visibility than later bulged canopies, but it matched the early Mark I character the restoration was built to preserve. The internal wing structures followed the same evidence base. The aircraft was rebuilt to represent the early 8-gun fighter configuration, including the structural bays and fittings associated with that layout. Any armament representation had to be compatible with civil operation and made safe, while still preserving the correct appearance and balance of an early Mark I fighter. Every visible and functional detail, from the special Dunlop tires to the cockpit equipment, was judged against the restoration brief wherever evidence and safety allowed. So the project became a disciplined attempt to return an early Mark I Spitfire to the air in the most authentic form practical. With the early Mark systems newly fabricated and the airframe rebuilt, could the resulting aircraft meet the stringent airworthiness demands of modern flight? The path from acquisition to flight stretched across many years, but by 2014, the static historical evidence had been transformed into a dynamic flying machine. The transition from a quiet workshop reference to a running, vibrating aircraft introduced immense mechanical stress. Modern flight regulation required the rebuilt ex-military fighter to prove material strength, system reliability, maintenance control, and operating safety within the appropriate Civil Aviation Authority airworthiness and permit-to-fly framework. Replacement parts, newly manufactured components, and old systems all had to be substantiated through approved processes while the historic configuration was preserved wherever safety allowed. Before the aircraft could leave the ground, the team had to complete ground runs, systems checks, inspections, and the approval steps required for a high-performance ex-military aircraft. The cooling system, undercarriage system, controls, engine installation, and fastened structure all had to be proven safe enough for test flying. Once those checks and approvals were complete, the aircraft was cleared to return to the air. On March 26, 2014, the aircraft was rolled out onto the active flight line at the Duxford airfield. This was the airfield most closely associated with its number 19 squadron service, and the place where the restored aircraft's story could reconnect with its wartime unit. The airframe was painted in its exact 1940 squadron code markings, displaying the letters Q and V on its fuselage sides. The engine was primed and started, pulling the aircraft down the runway and lifting it back into the operational airspace. The successful test flight demonstrated that the restoration had produced an airworthy early Mark fighter, one that could fly again while preserving the character of its 1940 configuration. However, operating a highly specialized, reverse-engineered machine presents an ongoing mechanical trade-off. Every hour flown consumes the limited lifespan of the newly fabricated moving parts, subjecting the historical replica to general mechanical wear and the inherent hazards of active aviation. Maintaining a vintage aircraft in an airworthy condition requires continuous intervention. The fluids must be constantly cycled to prevent internal seal degradation, and the load-bearing spars must be regularly inspected for early signs of metal fatigue. Recognizing this severe operational limit, the owners executed a final procedural decision to secure the long-term legacy of the aircraft. In the year 2015, Thomas Kaplan and his family donated the machine to the Imperial War Museum and the nation, securing it within a public collection under the donor's wish that it remain at Duxford in airworthy condition. Under Imperial War Museum ownership, it continues to appear at displays at Duxford and elsewhere. The aircraft survives today as a public mechanical document, its recovered evidence, rebuilt structure, and early Mark I systems held together as a single legacy. The Duxford restoration did not erase the wreck's history. It converted that history into a working reference for one of the earliest combat Spitfires to return from loss, burial, corrosion, and reconstruction.